So hey guys, welcome to the channel Learning Comparative Programming with CodeChef. So if you want to learn comparative programming and master data structures and algorithms, this is the prime location for you. Every week there are several videos regarding the contest of CodeChef platform and regarding various concepts of comparative programming. So if you are new to the channel, then please do subscribe to the channel and turn on the bell notification. Myself Chirayu Jain, I'm a CodeChef educator, and the problem that we are going to take today is watching CPL. Right, with the code WIPL, and the prerequisite of the problem is 01 knapsack. So let's get started with the problem. Okay, so the problem that we are going to discuss is watching CPL. Right, so we'll read the problem statement. So we have CodeChef Premier League, and in this we have Mike and Tracy who want to watch grand finale, and there are some conditions given. So let's directly jump on to the main context. That is, we have a field where match is playing, and we have a wall that is of height k. Right, so we have the field, and we have a wall over it which is of height k. Right, so let us suppose that this is the wall of height k, and outside there are n boxes which are numbered from 1 to n, and each box has a certain height which is represented by h of I. Right, so there are certain boxes and each boxes is of certain height. Right, it is not particular that we have been given of a certain kind of order. It can be any order, and the height is hi for a particular box. Now Mike wants to take some boxes and stack them on the top of each other to build two towers. Right, so Mike wants to select some of the boxes and want to build two towers out of them. The height of each tower is the sum of the heights of the boxes that form it. Right, so the overall height of each tower will be the sum of the height of the boxes. Let us suppose that this is a tower. So we have certain heights of each box. So sum of the heights of each box, right, will be the height of the total tower. Of course, no box may be in two towers, right? So we cannot select a same box in the two towers. The height of each tower should be at least k, right? To see the match from this particular level, we have a wall of height k. So at least the height should be greater than or equal to k to watch the match. Right, to watch the match, it is the given condition that the height of the overall tower should be greater than or equal to k to watch the match. Right, then Mike can climb on the top of one tower and Tracy on the top of other, and they can watch the match uninterrupted. Right, so if we have two towers which are of height greater than or equal to k, then we can easily watch the match. Right, while Mike is busy with stacking the boxes, Tracy would like to know that the smallest number of boxes required to make the tower, and each of them has height at least k. So like Mike is building the tower, so Tracy wants to know that how many minimum number of boxes that we require to make these two towers such that their height is greater than or equal to k and they can watch the match. Right, so she wants to know how many boxes are required at minimum. So we need to help Tracy to find that. This is the overall problem statement. So let us suppose that we have been given this particular example input. Right, for the two test cases we have two things. Right, first one is the number of boxes that we have, and the second one is the value of k, that is the height of the wall that we have. And in the array that we have been given, there are the heights of the boxes that have been mentioned in a random order. So the height of the boxes which are present are in the random order. There is no particular order which has been given, either increasing or decreasing. They can be in any particular order, and we need to find the minimum number of boxes. Okay, so let us understand the samples. Right, so if we have this particular sample, so here are the number of test cases, and for each test cases we are getting two values, that is n and k. Right, so k is 38 and n is 8, and this array is denoting the height of each box. Right, so we have in all 8 boxes, and the height of the ith box is this. Right, so if we want to form two towers, what will be the approach that we'll think first? We will think that in each tower we'll try to get as many boxes, as many high boxes. That means the length of each box must be maximum to allocate less number of boxes at each tower. We will think greedily. Right, so to accumulate boxes in one tower, we'll try to get as many high length boxes as possible. So what we will do, we'll sort the array for that. Right, so after sorting the array, what will be the product? That is 7, 7, 7, 8, 8, 10, 19, 20. This will be the sorted array, and we'll try to traverse this array and get as many boxes in one tower as possible. So let us suppose that in first tower we'll include this particular box that is of height 20, height 19. So we'll get a tower that is of height 20 plus height 19, that is 39. So can we watch the match? Of course, because the value of k is 38, so we can watch the match. One tower is fixed. Now if in the next tower we'll include a box of height 10, then 8, then 8, it sums up to, that is 26, and then 7, 33, and then 7 again, so it will take, that is height 40, right? So till here we'll include the boxes, and these are the boxes that will be required in making 2 towers. There are certain other permutations also, such that we can take like 20, 10 and 8 together to form a tower of 38 height, and then 19, 7 and 7, like any possible combination can be fulfilled if we take certain values, and the minimum number of boxes required will be 7 in this particular case, right? Similarly, in the second case also, like if we sort the array and think greedily, that is 2, 4, 9 and 10, so 2 boxes will be required, that is of height 9 and of height 10, to watch the match, because the height of the wall will be 5, that is very low. So only 2 boxes can fulfill our condition. But is this approach good? Is this approach be fulfilling? Because if we think greedily, can there be some test case lagging? Let's see. So if we take a certain test case, let us suppose that if we take this test case, we have 5 5s and then 10 and then 20, and we are taking the height of the wall as 25, so k is equals to 25, right? So now if we want to allocate 2 towers like in greedily method, so what will be the number of boxes required? That is of height 20 and 10 for the first tower, which will make a tower of height 30, and 5 5 5 5 5, all the boxes will be consumed. So because it sums up to 25, so it will form a tower of height 25. So all the boxes will be consumed. That means the answer should be, that is 5 plus 6, 7. The answer must be 7 according to this. But is this the efficient answer? Let's see. So if we take the box of height 20 and a box of height 5 together, it will sum up to 25. It can be formed as a tower. And if we take 10 and if we take these 3 boxes together, that is 5 5 5, so 5 5 5 plus 10, it will be 25. So we can form 2 towers which is of height 25 and 25, and still there is one box left. So in all, how many boxes we have used? That is 6 boxes we have used. So it is a more efficient way. We have figured out a more efficient way rather than just greedily selecting all the boxes after the sorted array. So this particular thing derives that the solution is not greedy. We have to think of all the possible combinations that we have, and whenever we need to search all possible combinations and select the best possible suit that we have, the best possible path that we need to have, we'll think of dynamic programming approach. So this is how you judge that the problem is dynamic programming problem, right? So after striking in the mind that we can think of greedy approaches and then deriving to a result that this problem cannot be solved greedily because there are certain conditions which are required in the problem and we need to check every possible combination, there is the striking point where you can judge that the problem is dynamic programming problem. Right, so this is the point where we can see the dynamic programming problem. And if you want to learn more about dynamic programming problem, then you can go to Unacademy platform as well, right? It is the best platform. You can go and watch free videos out there. You need to just register and use my coupon code, that is Chirayu Jain, and you can watch free lessons over there, and even you can subscribe for Unacademy Plus. That's your choice. But there are very good prime educators who can teach you these all concepts very easily. Okay, so now let's try to formulate the approach in a stepwise manner, right? So first of all, we'll form the DP solution, the DP array that we require, and the DP of I, S denotes that the minimum height greater than or equal to s, which is formed by the last I elements, right? So the height which is formed by the last I elements, right? After we have sorted the array, we are taking the boxes of height in a decreasing manner, right? Starting from the right end of the array, that is the largest box, we are taking the elements, and the dp of I comma s states that if we take last I element, that what is the minimum height greater than or equal to s that we can get, right? So if we take the last I elements, so this is the first thing that I want to discuss, that what is the state we are looking at, right? And the things that we'll select is from 01 knapsack, as this is the prerequisite of this particular problem, that is 01 knapsack problem. So how we can select the particular box? We'll select all the possible permutations. When we form the recursive approach of 01 knapsack, what we will think that first of all we'll include this box, and the second thing is we'll not include this box. These are the only two options that we have for a particular box. So this is how we will think. First step is, first recursive call, if we want to develop a recursive solution, is that we'll include this particular thing, and the second recursive approach will be not including this particular thing. So these are the two opinions that we have while we solve 01 knapsack problem, and then we formulate over the tabulation method, right? So if we have got that we will select these boxes out of these I elements to form a particular tower, then how we will find that the remaining boxes will sum up to the tower of the second height, or the tower of the second height will surpass the value of k. How we'll check that? So for that, what we will do, we will form a suffix array, array which will store the suffix sum till a particular ith element. So what will state that we will also calculate the suffix sum of the height in the sorted array, that we have formed the sorted array, and we'll form a suffix array as well. So what will the suffix array storing? That the sum of the height of the last I elements. So what will be the benefit for that? So if we have the suffix of the sum till the ith position, and we also know that what are the boxes that what are the height of the boxes that we have selected in this particular state, like if we have selected last I boxes, and what will be the what will be the height if it just surpasses k, greater than or equal to k. So we know in this particular thing, that is dp of I comma k. So if we subtract these two, what will result? The suffix I stores all the boxes till I, and this box and this particular value stores that what will be the height of one particular tower. So if the difference of these two, the remaining difference, is greater than or equal to, sorry, it will not be 0, it will be k. So if it will be greater than or equal to k, that means that we have sufficient boxes which can sum up to k for the next tower. This only signifies that, right? So if that is greater than or equal to k, that means from the last we have reached a point where we have sorted some of the boxes for the first tower, optimized boxes, right? And the remaining boxes which are remaining from this particular set is involved in the next tower, which is of height greater than or equal to k. This signifies that. And whenever it signifies that, that means these only, the remaining last boxes are the optimized boxes that we require for this particular solution. So what we will do, suppose we have n boxes here lined up, and at this particular ith position, I have found that the suffix, the sum of all the boxes minus the boxes that we have selected for any of the tower, any of the first or the second tower, the subtraction of these two, the remaining boxes are greater than or equal to k. That means we can form another tower as well. So the total number of optimized boxes that we'll require is these number of boxes, that will be n minus I boxes for the particular ith value. So what we will return? We'll return n minus I. And if this condition doesn't hold throughout the array, then we'll return -1, because there is no possible combination that can form the two towers. So this is the simplest approach that we can think, using 01 knapsack prerequisite and a suffix sum that we have additionally added to the variant of this 01 knapsack, right? Now let's try to form the DP table of a particular thing and clear out this approach effectively. Okay, so now let's try to fill up this table and formulate a solution, right? So we have this particular heights, right? So what we will do, first of all, we'll see the height in the sorted order. So we have sorted all the heights, right? So it is this particular order, and first of all we'll try to form the suffix sum. So what will be the suffix sum? That is, first of all, the height, maximum height 10, and then 10 plus 9, that is equal to 19, and then 10 plus 9 plus 4, that is equal to 19 plus 4, that will be 23, and 23 plus 2, that will be 25. This is the suffix sum array that we are looking at, right? We'll use this array after developing the whole DP table. Now, how we can develop the DP table? The first and the important condition is we'll fill all the DP values with maximum so that we can easily compare, and whenever we need to find the minimum of any two values, we have sufficient spaces so that the values which are exceptional and which are beyond the range can be easily managed, right? So we'll use maximum for that particular case, and we'll try to form the solution from this particular value, right? Like starting from the highest value that we have. So in this portion we are storing the values of k that we can vary from right from the 0 till the value of k that we have in the solution, that is 5, and here we are taking the heights, right? So if we fill that for a particular height, this particular height 10, how many boxes are required for the value k, right? So if the value is just greater than or equal to k, that means greater than or equal to 5, then how many I boxes do we require here if we take 10? So we can take only single value 10 and formulate this particular solution, because 10 is greater than or equal to 5, right? So 10 is greater than or equal to 5, and we can take only single box 10, and then we can easily form this and we can easily watch the match. So what will be the height required? 10. So the condition that is developed is that if this particular let's suppose that we are traversing over j for a range of value k, so if j is less than or equal to, that is height of I, then at dp what we will store? That particular height of I only, right? So, because using that particular height we can easily watch the match. Why will require another boxes? So like 5 is less than or equal to 10, so we'll easily watch the match using this particular box only. So 4 is also less than or equal to 10, we can watch the match using this box only, like this. So this is how typically we solve the knapsack problems, right? Same case here for 9. Same case here for 9, that is using 9 also we can easily watch the match, right? So we'll fill this array up with 9, right? This particular portion will be 0, of course, because it is beyond this beyond the limitations, and for the k 0, what will be the number of boxes required, because we do not have a certain height, so it will be 0, right? So typically we are forming up till here only, right? So we need not to consider this particular portion. So from the height 10 only, from the height 1 only, we are forming up the things, right? So we will not consider this particular array as of now, right? So we are looking at this particular constraint and how we'll able to resolve that. Now for the height 4, we see that we have the value of k as 5, so we cannot just directly copy 4 over here, we need to think of something, right? So as I've discussed in the approach, that while we are using the knapsack approaches, we have only two options left: either we'll include this box or we'll not include this box. So if we'll not include this box, then what we will do? We'll just take up the previous thing that we have just stored now. So what is the previous state that we have just stored now? That is this state. For this particular value of k, what is the previous state that we have? That is this particular state. So we'll not include that box. But if we include that box, then what will be the state, right? So what will be the state? That if we subtract this particular weight, that is 4, from 5, 5 minus 4 will be resultant into 1. So at this particular 1 weight, if we add this 4, then it will sum up to 5, and that is the bare minimum possible height that we just require to see the match, right? So we'll require this 4 box at just height 1 so that we can watch the match, and the value which is stored at this particular DP state, that is 1, which is referring over here, and for the particular value for the particular previous state, that is 9. So what will be the height required? That is 9 plus the height that we are including, that is 4, right? So at this state, at one state, if we add this particular height, that is 4, then we'll develop one thing, that is we are including this particular height, right? At the state 1, we are adding this particular 4. At the state 1 of the previous state, we are including this 4 so that we can include the height, and the effective solution will be 9 plus 4, that is 13, So we'll require these two boxes to form this resultant height. But if we not include this box, then what will be the state? That is only this state, because we haven't included anything. So what will be the minimum of these two? The minimum of these two will be 9 only. So we'll select that if we include this box, then what is the value that we are getting, and if we not include this box, then what is the value we are getting, and effectively we'll find the minimum out of that. So if we will not include this box, then the answer will be 9, and if we include that, the answer will be 13. So minimum of these two will be 9 only. So like maintaining the same color, so it will be 9 only here, right? For every possible things we'll check that, right? So for the value of 4 also, since the 4 is less than or equal to height of I, this condition encounters, and simply will copy 4 4 4 from here, because all are less than or equal to 4. Now when we move towards 2, what will come? 5 is not less than or equal to 2, so again we need to check the I plus 1th state, and we'll subtract 2 from 5 and it will come 3, right? So at the third state we'll check, then what is the value? That is 4, plus what will be the height required? That is 6. So that is 2. So 4 plus 2 will result into 6, and the minimum of 9 and 6 will be 6. So here we'll form 6. Here we'll form 6. Then again we'll check at this particular position, that is 4. So 4, what we will do, we'll subtract 2 from it. So we'll check this particular state. Now 4 plus 2, that is 4 plus 2. If we take this state and the height 2, that will be equal to 6, and the I plus 1th state is 4. So minimum of 6 comma 4 will be 4. Similarly for this, 3 minus 1 will be equal to 3 minus 2 will be equal to 1, and the value stored is 4. So minimum of 4 plus 2, that is 6. 6 comma 4 will be 4. So here we will have 4. And at this condition now, what do we have? We'll have that it is less than or equal to height of I. This condition will be encountered. So we'll just copy the value, that is height of I, that is 2, because this is the only box that will be required. So now we have formulated this TP array, and we are considered only for the value k, that is this particular 5. We are only considered for this particular 5. So we'll compare these values with the suffix, that is 6, 9, 9 and 10. We'll compare these values with the suffix sum. So what will be the difference of this particular two values? That is 0. But what is the height that we require? That is height, the value of k should be equal to 5, so it is not coming, so this will not be the I. The difference of these two values is 10, and the height what we want is 5, so it is just greater than or equal to k that we require. So this is the possible I that we want. So what will be the condition? That is the value of indexes are 0, 1, 2, 3, right? So this is the possible I that we want. So the total heights are 4, and the value of I is 2 that we are getting. So 4 minus 2, that means only these two boxes are required. These two boxes are required. So the 4 minus 2 will be 2, and that is supposingly our answer, right? So this is the possible approach. We have filled the table and we have formulated a DP approach using 0-1 knapsack. It is a perfect variant of 0-1 knapsack, where we try every possible thing. We'll include the particular box for a tower, or we'll not include the particular box for a tower, and try to get this approach done. Okay, so let's see the code. So as we have discussed in the approach, that what we will do, first of all, we will enter for each test cases two values, that is n and k, and we'll make two separate arrays for height and suffix, and then a DP array of size n plus 1 cross k plus 1. Then we'll enter the height and we'll sort the array, right? And we'll traverse the array from the back, right, to take the maximum height boxes as possible, right? So first of all, we'll initialize the suffix of n from 0, because from n minus 1 we'll enter the values, right? Because we have created a suffix array for size n plus 1. So for I equals to n minus 1, I greater than equal to 0, I minus 1s, we will form the suffix array, as we know how to form the suffix array. And then for each and every block, for each and every cell of DP, we'll initialize it with max, right? The DP of n comma 0 will be equals to 0, as we have seen that part is 0 in the approach as well. And this is the important condition that we are going to discuss. So as we have discussed in the approach, while we are writing the values for each cell, then if the j, that means for the k values that we are traversing around, if it is less than or equal to height of I, that means that only box is sufficient to watch the match, right, for that particular value of k that we are traversing using the value j in the columns part. So the dp of I comma j will be equal to height of I, and we'll continue that. And if there are two possibilities, either we'll take that box or not. So if we are taking that box and that particular box in the I plus 1th state is equals to max, that means beyond the certain boundary, right? So that means we'll initialize dp of I comma j as max as well, right? Because there is nothing to compare right from that particular boundary. And if this is not true, then what we will do? We will take the minimum of the I plus 1th state if we are not including that box, and the I plus 1th state and j minus the height of I, as we do in the traditional knapsack portions, right? J minus the height of I to check the previous state, and then add that particular box, that is the height of I. So this is the important condition over here, right? This is what we will do. So these are the three important conditions for filling the knapsack portion and selecting the box for a particular tower. Now what we will do, as we have formed the suffix array, so we'll check the important conditions that we have just used in the step number 3, that will subtract the suffix portion, the ith portion of that suffix, with the dp of I comma k, where dp of I comma k represents that we have selected the last I elements and the sum is just greater than or equal to k, right? So if the difference of these two is greater than or equal to k, that means that we can form another tower of height k as well. So we'll form the largest I as possible, and then whenever we got that I, what we will output, we'll output n minus I, because that is the remaining boxes, that is the total number of boxes we have selected. So for this particular ith portion, the remaining boxes that we are traversing from the right hand side of the array will be the boxes. So n minus I will be the possible solution for that particular configuration, and we'll break down from the solution. Otherwise, if we are not able to find any particular I, then what we'll output, that means there is no configuration possible to form the two towers, so we'll output -1. So this is how the whole code is working for this particular problem, and if we run this particular code, then the answer is coming 7,2. That is the required result in the portion that we have for the sample test cases. And now it's the time to submit this particular code on CodeChef. So we'll select the code. Okay, so let's try to submit this. And we got AC.